Commonly, the water distribution system analysis and design involves a series of normative operational scenarios, which as designers of these systems we must consider to ensure that the network we are designing will achieve a minimal performance in each case. The most common scenarios are the following two. The first one, which generally determines the pipe's size, is when the demand of the network corresponds to the maximum possible, the peak hour demand. Under this scenario or demand hypothesis, it is usually established that the design of the water distribution network guarantees that the pressures of the nodes are within a specific range. This range is also defined by the applicable standards. If you have followed this series of videos, you will know that, at this level, we have already dimensioned the water network for this first condition. Looking at the base hypothesis, you will see that here we entered a peak demand factor equal to 2.5. From this demand condition, we have allowed the software to automatically define the pipe section's diameters in our water network. The second scenario or hypothesis is when the water network's design, performed under the peak hour demand scenario, is verified for a fire flow plus a maximum day demand. In such cases, the design codes usually require that you define one fire hydrant as the most unfavorable so as to assign it as the design's fire flow. In the rest of the water network's nodes, the demand is somewhat lower than the peak hour demand and is usually, as I have previously said, equal to the maximum day demand. The water network verification under this second hypothesis must, in order to consider the design valid, result with pressures again within a range, and it is also necessary that the pipe's flow velocities do not exceed a certain value. Regardless of the factors that the design codes of your country establish, surely the procedure is quite similar to what I have described, and according to this, we intend to show you how in our AQUEDUCTS software you can perform this verification using the calculation hypothesis. In this way, if we are going to carry out the verification for fire flow condition of this water network, the first thing to include in it are the fire hydrants. Although the hypothesis may require that you assign the demand to a single hydrant, in any case it is part of the water network design that you provide the location and amount of required hydrants to cover this network's area of influence. In our case, we are going to add two new nodes that later will be converted into hydrants. We will locate the first one at this point. So I select Add Node, click on the pipe section, and insert it. From this one I create a pipe section to the north in this way. Now let's edit this new node to make the necessary modifications. First I modify the name in order to identify it in the tables of the software, North Hydrant, in this case. Then, the most important thing, I tell AQUEDUCTS that this node is a hydrant type. This allows several things. The first one, as you will see in a moment, is to give the corresponding drawing symbol, which is a requirement of any project document. The second is that it will allow us to quantify the corresponding fittings in the lists of materials. And the third is that it allows us to indicate to the software that this component must be treated in a specific way in the hydraulic calculations based on the creation, application, and comparison of the calculation hypotheses. Note that, despite having made the change, the option of placing a water demand is available here. The first thing you will surely think, and it is an option you have, is that you must enter the fire demand here. But, since I intend to use the software's hypothesis concept to evaluate the operation under fire flow, I will keep it at 0. Finally, I assign to rain and node elevations, necessary to account for excavation volumes and, of course, to calculate the pressures in the water supply network. I close the dialog, And there we have our first hydrant symbol. I'll repeat the sequence with another hydrant here to the south. Now we have everything arranged in the water distribution network to carry out the fire flow verification. At this moment, as you see, we are with the base hypothesis. Performing the calculation at this time, there would be no change with respect to what we have already done, since the hydrants have zero consumption. In fact, since there are no losses, given that the flow is zero between the network and the hydrants, it is to be expected that the piezometric at the pipe's end be the same, resulting in the pressures that you observe here. Note that the pipe table precisely indicates that the flow is zero in the pipe sections that feed each hydrant. Let's go to the Calculation and Design panel on the Water Network tab and click the New Calculation Hypothesis button. In the dialog, we assign a name. And, as I mentioned, under this hypothesis it is expected that the potable water consumption of the network is somewhat lower than the peak hour flow. Therefore, I will introduce here a factor of 1.8. That is, we are assuming that the water network demands almost twice the average flow at the time of a fire. Let's enter a description to know what this hypothesis is about. Then, and this is where we begin to find the advantages of using the calculation hypotheses in the software, we go to the Nodes tab to indicate that in this hypothesis one of the two hydrants will have the normative fire demand. The procedure then consists of locating the node to which we wish to apply some modification. If it is a simple node or a hydrant, we can only modify its demand. If it is a fixed head node, we can only modify its piezometric. So, assuming in this first analysis the most unfavorable hydrant is the north one, I activate this box to unlock the demand field, and enter 16 liters per second as a fire demand. I keep the changes and close the dialog. Here I must ensure that I have the fire flow hypothesis active. Click Calculation to see the results after closing the message. The first thing we see is that, effectively, the 16 liters per second we have defined as fire demand goes to the north hydrant. Certainly, this velocity is excessive and we will have to decide whether to modify the diameter according to what the design code set. But let's go to the table of nodes because what is mainly interesting here is to see the resulting pressures. We see that, in the north hydrant, we have a pressure of 15.26 meters which, despite being low, is still above the minimum that we have defined in the configuration of the project. So, preliminarily, we could say that the network verifies under this consumption pattern. I will choose to modify the diameter of the pipe that feeds the hydrant, but ensuring that the development of diameters in the feeding route is always downward. So I will also modify the one in this pipe section. And if I redo the calculation now, we'll see for sure some improvements. We see that the pressure is now in the order of 20 meters in the hydrant. Much better, obviously. Well, we have already checked the network assuming that the hydrant to the north is the most unfavorable. Let's now check it, assuming that the most unfavorable is the south hydrant. I could create a new hypothesis, but in reality, complicating this project is not justified. Therefore, what I will do is to change the node in the hypothesis that I have already defined. Note that, when deactivating the modification option in the north hydrant, I do not worry about modifying its demand since the software will automatically update the value to what is defined in the base hypothesis, which is 0, as you might remember. Now I activate the option for the south hydrant, assigning the fire flow. When we repeat the calculation, we see that now water does not enter to north hydrant, and that to the south hydrant, the 16 liters per second required for the fire are conveyed. In this case, of course, without having changed diameter values yet, we see that if the fire should be handled by this hydrant, the pressure is below the minimum of 15. So in reality, the most unfavorable hydrant in the supply network is the south one. I check the diameters in the hydrant feeding routes and modify them, if necessary, to take it to 110 mm at the entrance to it. Finally, I recalculate. Despite the modification and being in the recommended range of velocities, we see that in any case the pressure in this hydrant is the lowest, thus certifying that it is the most unfavorable of the network. We could say that at this level the network is designed and verified for the fire flow hypothesis. Notice that now, in the properties of the hydrant node, it appears to be counted correctly in the list of accessories. The last thing I want to present to you regarding the software's calculation hypotheses is the option that you have of being able to compare, at the table's level, the results between two of them. I'm going to place the base scenario as the current hypothesis and, to update the table, I click the calculation button. And here below, in the Compare with Hypotheses list, I will select the fire hypothesis that we have previously created. Note that, when making the change, automatically the columns with comparable values in the tables are duplicated. We have now listed the water demands and pressures for both hypotheses in order to be able to compare them, if required. Note that the initials of the name of the hypothesis, B, H, are placed in the header for basic hypothesis. F, C, for fire check. And, in the pipes table, you will see double columns for diameter, coefficient, flow, and velocity. In this way, it is easier not only to do the comparison and analysis of your designs but also the generation of the project's corresponding descriptive memory. And that's all for the moment. You will see that you have simple options to design and verify water supply networks with our software. Until the next video.